Hello everyone, now we're going to solve Cambridge IGCSE Physics, May, June 2025, paper 4-1. 1A. Circle the vector quantities in the list. So vector quantities are the ones that have direction and magnitude. So acceleration is a vector quantity, mass is not, speed is not, time is not, so velocity is. B. Figure 1.1 shows the speed-time graph for a train traveling from station A to station B. 1. State the maximum speed of the train. As you can see, the highest point is right here, and that is about 56 meters per second. To describe the motion of the train between station A and station B. So firstly, you can see that speed increases and the gradient is constant, which means the acceleration is constant, and then it reaches the constant speed of this much and then decelerate, which is constant. So we're gonna have to write, firstly, it accelerates at a constant rate and travels at a constant speed. Then it has a constant deceleration. 3. Calculate the distance between station A and station B. So we have a speed-time graph, so distance is the area and the graph. So this is a trapezium. We can find the points first, right? So this is about 80 and 56. This is 500, so 480, 56, and this is about 530. So we can find that's just right here, right? So area of trapezium is equal to 0.5. These two, 530 plus 80 to 480, so that will be 400 into height is going to be 56. So if we put that in calculator, 530 plus 400 into 56, this is equal to 26040, which is about 26,000 meters in two significant figures. We are supposed to write this working down here. Okay, so on a different day, the train takes 650 seconds to travel between station A and station B. Suggest one change to the motion of the train that leads to this longer journey time. So longer journey time means lower speed, and one that causes the lower speed is maybe low acceleration and things like that. So we can just write in general, lower average speed. 2A. A resultant force is applied to an object moving with a velocity v in a straight line. State two different changes to the motion that the resultant force may cause. So resultant force can change an object's motion, but how, right? We can change its magnitude of speed or velocity, right? So you can change magnitude of velocity or maybe in direction. To state one other way that forces may change a stationary object it can not only affect the motion but also like the size and the shape. You can say maybe when something force is applied and an object is squashed, things like that, right? So it can change an object's size. B. Describe how a uniform meter ruler, a pivot, and a selection of masses can be used to demonstrate that there is no resultant force on an object in equilibrium. You may draw a label diagram in your answer. So this is testing about moment. And in a typical experiment of a moment, we have a pivot and a uniform meter ruler, which means that its center of mass is in the middle, which means if we put that center on a pivot, then we don't really need to consider its weight, because like its weight is here and pivot is acting like this. These two forces cancel out and they don't affect the moment at all. Okay, so let's just say this is a uniform meter ruler. Like say this is 0.5 meters and 0.5 meters. You don't really have to write that. Okay, so and we have a selection of masses, which means we can like put mass here, somewhere around here, and then we know the mass, right? So if we know the mass, we know the weight or the force, and then we know the distance between these two and calculate the moment, and this will act in a clockwise direction, and this will act in an anti-clockwise direction. We have to show that this clockwise moment and anti-clockwise moment is equal, so that an object does not have a resultant moment. Okay, so firstly we write to place the center of meter ruler on a pivot, and then add a mass on one side of the ruler and another on the other. Then calculate the moment using the equation. Moment is equal to force, which is weight of mass in this case, into perpendicular distance from pivot. And now we know that the moment in the anti-clockwise moment is equal to clockwise moment. There is no movement in equilibrium. Figure 3.1 shows a side view of part of a concrete track at a skateboard park. A skateboarder is initially at rest at point A. The skateboarder then travels through point B and comes to rest at point C. Describe the transfer energy as the skateboarder travels from A to B to C along the concrete track. So firstly, right, this is the initial point. And if we are on a height somewhere like up there, then we have this thing called gravitational potential energy. And as it moves, right, this GPE will be transferred to kinetic energy, and then because it is like moving across a concrete track, there will be some kind of friction which has to be overcome, and that will be transferred to some thermal energy as well, and returned here. So that's why it can't really move until up to here, right? because some of the energy will be transferred to, like, lost to thermal energy. So we can write something like gravitational potential energy is transferred to kinetic energy as it moves as they move down. Then kinetic energy will be transformed to GP again. Some of the energy is also transformed to thermal energy. B1. B is at ground level and C is at 2.8 meters above the ground level. The mass of the skateboarder is 65 kilograms. Calculate the work done on the skateboarder as she travels from B to C. So work done is equal to force into distance. So we know that force is going to be just its weight, her weight. So 65 into weight, 9.8, distance is 2.8. If we put that in calculator, we get 1783.6, which is about 1800 joules. 2. The skateboarder falls off the skateboard at B. She hits the track and comes to rest after a few milliseconds. State the equation that defines force with which the skateboarder hits the track. State the meaning of any symbols you use. So this is indicating the change in motion, change in velocity, or otherwise change in momentum. So if you like hit or something like that, you need to consider about the impulse. So force is the rate of change of momentum. So you can say that F is equal to, we can write with symbols. So F is equal to rate of change of momentum. And we have to consider the symbols. So this is, you can say, impulse or change in momentum. And T is going to be time, like time taken when she hit. 4. Figure 4.1 shows the heater used to warm the air in a room. A1. State the main method of thermal energy transfer through the air in the room. Like that would be convection, because through the air, right? Yeah. Explain how the heater warms all the air in the room. So heater is placed on the ground because warm air, it rises. So you can say warm air rises due to low density. You can compare lower density than cool air. And as it rises, it will replace the cold air, right? So cool air is replaced by warm air and it falls. This cool air will be warmed by the heater and the process repeats. So this process is called, right, convection current. B1. The power of the heater is 2000 watts. One is connected to the main supply with an EMF of 230 volts. Show that the current in the heaters is approximately 8.7 ampere. So we need to know this equation, right? P is equal to IV, and 2000 is equal to 230 into current, and 2000 divided by 230 is equal to 8.69565, and so on, and that is rounded. That can be rounded to 8.7. To the plug connecting the heater to the main supply is fitted with a fuse. Fuse ratings of 3 amperes, 5 amperes, 10 amperes, and 13 amperes are available. State which fuse is used and explain your answer. So we have this 8.7 ampere, and which you have to choose the closest one, and that is going to be 10 amperes, right? So it is not like too high or too low. So you can say that 10 amperes it's if we choose the smaller ones like 3 to 5, it will melt before this actually gets the current that it has to. So if smaller rating is chosen, it will melt in normal, even in normal conditions. If larger rating is chosen, the heater will be damaged before the fuse melts if the current gets too high. So yeah. 5. A ray of light is incident on a soap film. Figure 5.1 shows a magnified image of a small part of the soap film. The ray of light is refracted as it enters the soap film. The refractive index of the soap film is 1.28. A define refractive index in the speed of light. So in terms of speed of light, which means you have this equation, N is equal to C by phi. So refractive index is the ratio of speed of light to speed of light in air to speed of light in a particular medium. In this case, it is the soap film. B1 showed that the angle of refraction as it enters the soap film is approximately 43 degrees. So we can use this equation, N is equal to sine I divided by sine R. Refractive index is 1.28. Sine I is this one, 60 degree, and then sine R. So you can put this directly into a calculator. So we get like 42.577, things like that. That is approximately equal to 53 degrees. 2. On figure 5.1, carefully draw the refracted light ray in the soap film and label the angle of refraction. So you will need a protractor. This is the normal, and Because the angle is about 43, it will be like bent towards the normal. Please use the protractor to draw this and put an arrow. This is about 43 degrees. See, the ray of light is monochromatic red light with a wavelength of 680 nanometers in air. To find my monochromatic, so it is the light of a single frequency. So to calculate the frequency of the light, we know the wave equation V is equal to F into wavelength. You can write lambda. V is equal to F lambda, and frequency will be equal to like the velocity of this light in air will be 3.0 into 10 power 8 meters per second. So we can divide it by 680 to nanometers is 10 power minus 9. So we get 4.4117, things like that, into 10 power 14. So we can just write 4.4 into 10 power 14. Unit is important, hertz. Figure 6.1 shows a person using a magnetic window cleaner. The part on the outside of the window is attracted to the inside part through the glass window. Each part of the window cleaner contains two magnets. Okay, figure 6.2 shows a magnetic field between the parts of the window cleaner. Okay, inside window, outside window, bar magnets handle. A glass is not a magnetic material. State the difference between magnetic and non-magnetic material. So, magnetic material will be attracted by a magnet. Magnetic materials are attracted by, attracted to a magnet, whilst non-magnetic materials are not. B. Suggest a suitable material for the magnets in the window cleaning. Explain your answer. So we need a permanent magnet. So we choose steel because it is a permanent magnet. C. Label the poles of the magnet in figure 6.2. So we know that it always like goes out from north to south. D. State how the field lines in figure 6.2 show different strengths of the magnetic field between the magnets. So here you see that those lines are right closer together, and it will indicate that the strength is stronger. So if one field lines are closer together, the strength of the magnetic field is larger. 7a. Figure 7.1 shows a sketch of the current voltage graph for a electrical component. Name the electrical component. So you can see that there is no current in this negative direction, but only in the positive direction. So this is clearly a diode. Explanation, I just said it. There is only current in a particular direction as the voltage increases. Draw the circuit symbol for this component. diode looks something like this. B. Figure 7.2 shows an electric circuit for two identical electric heaters, A and B, connected to a main supply of 230 volts. S1 is closed and S2 is open. The reading ammeter is 3.9 amperes, which means this is like, you can forget about this. The circuit looks like this. So V is equal to I and R is equal to 230 divided by 3.9. That will be equal to 58.97 something. So you can round that to two significant figures, 59 ohms. So calculate the energy transferred by heater A in 5 minutes. So energy is equal to PT, which is equal to IVT. So I is equal to 3.9, V is 230, time is going to be 5 into 60, don't forget the 60 is for seconds, and 3.9 into 230, 5 into 60, that will be 269100, which is about 2.7 into 10 power 5 joules. Three, S1 remains closed and S2 is closed. Determine the reading on the ammeter. Show your working. So these two are closed, and ammeter is in series circuit for both of these branches. So it's not just particular to one of the branches. You have to consider for the whole circuit, right? So we know that I is equal to V by R. We know the voltage, and we need to know the resistance. So resistance is 59 ohms for each component, like they're two identical, right? So this one will have 59 ohms, this one will have 59 ohms, and we need to calculate the resistance in the parallel circuit. So you can see 1 by R is equal to 1 by 59 plus 1 by 59, and R is going to be about 59 divided by 2 is 29.5. So we can 230 divided by 29.5 is equal to about 7.7966, which is about 7.8 amperes. 8. Figure 8.1 shows a diagram of part of a simple AC generator. A1, identifying components A and B. So A is a carbon brush, and B is slip rings. Yeah. 2. Component C is made of soft iron. Describe the effect of this component on a generator. So soft iron is usually used to link the magnetic field, and it strengthens the field since the magnetic material, right? So it strengthens the magnetic field of the magnet. B. The coil of generator rotates at a constant speed of 2 complete revolutions Okay, so 2 complete revolutions per second. Sketch a graph of the EMF generated against time on the x-axis on figure 8.2. The coil is in the position shown in figure 8.1 at time 0. So this is the coil of wire, this is magnet, and if this is in this direction, this will start with the maximum, because in that position, that perpendicular position, there is the highest rate of change of magnetic field. So we will start from the highest, and then it shows that constant speed of 2 complete revolutions per second, which means one revolution will take about 0.5 seconds. And since we start from here, this will be kind of like a cosine graph. We need to touch it. Lowest at after half, and then it will increase again, then highest. Looks something like this. See, in power stations, transformers are used to step up voltage of electricity generated before it is transmitted through cables over long distances. 1. Explain the advantages of transmitting electricity at high voltages. So for transmitting electricity, we have to consider the power loss along the way. So power loss is equal to P is equal to I squared R. So if the current is, you want the power loss to be lower, so current has to be low. And we have to also this equation P is equal to IV. So if current wants to be low, then voltage has to be high. So this is the concept. So we can write that for less power loss, there has to be low current, according to P is equal to I squared R. 2. A power station generates electricity at 25,000 volts. A transformer steps up the voltage to 300,000 volts. The primary coil of a step-up transformer is 450 turns. Calculate the number of turns on the secondary coil of the transformer. So if a rough idea, right, because it is a step-up, the number of coils has to be greater than this. And we have this equation, and as to n divided by P is equal to Vs divided by Vp. So if we want Ns, number of coils, so 450 into 20, this is going to be secondary coil voltage, so 300,000. So if you put that in calculator, you get 5,400. Now, strontium-90 is a radioactive isotope that contains 38 protons and 52 neutrons. Strontium-90 decays to form an isotope of yttrium by emitting beta particles. A1 suggests how the nucleus of a stable isotope of strontium differs from a nucleus of strontium-90. Explain your answer. So This, because it is an radioactive isotope, this is not stable at all, which means there are more neutrons than the actual like stable isotope. So you can say that radioactive isotopes have more neutrons than the stable ones. More means like a lot more. Excess. And for explanation, if you have like more neutrons, excess of neutrons leads to instability, or you can say radioactivity. To complete the nuclear equation for the decay of strontium-92 tritium. So this is beta decay. Beta is just an electron, so -1, 0. And equations, right, have same number on both sides. So 90 plus 0 is 90, and then 39 minus 1, 38. 3. Explain why scientists limit the amount of time they exposed to radioactive strontium, because it emits radiation, right? So this ionizing radiation can be harmful to human cells. So we can write something like they emit ionizing radiation, which is harmful to human cells. B. Yttrium is also unstable. A scientist places a sample of yttrium near a radiation detector. Table 9.1 shows the count rate recorded by the detector as the sample decays. Figure 9.1 shows a graph of the count rate due to yttrium against time. So I'm assuming this will have the effect of background, but yeah. 1. Use figure 9.1 to determine the half-life of yttrium. Show your working. So half-life is the time taken for the count rate to become half of it, right? So we need to consider half of 48. 48 divided by 2 is 24. Look at the time for 24. And since it asks to show the working, you have to draw those like tracing lines on the graph. And this is about like this. Oh. So like there are 5 squares for 20 hours, which means 1 square will represent 4. So since this is about here, we can say that it is about 76 hours. To explain the difference between the count rate and the count rate due to the yttrium plotted on the graph in figure 9.1. So I just mentioned that the table values include background radiation. Table values. Background radiation. Okay, 10. Jupiter and the Earth are planets in our solar system. A. Describe the composition of Jupiter and the Earth. So composition, right? Jupiter is a gaseous planet. So we can say gaseous, and this is rocky. B. The gravitational field strength at the surface of the Earth is approximately 9.8 newtons per kilograms. gravitational field strength at the surface of Jupiter is approximately 23 newtons per kilogram. Define the gravitational field strength. So gravitational field strength, if you can just think about the equation as well. Field strength is like this. Unit will give a hint, is the force per unit mass. To state one factor which causes the difference between gravitational field strength at the surface of Jupiter and the gravitational field strength at the surface of the Earth, it is the mass of those planets themselves. So you can write mass of the planets. C. State and explain the difference between the orbital speed of Jupiter and the orbital speed of the Earth. So orbital speed of the Earth will be larger, will be faster for the Earth because it is closer to the Earth. So Sun is closer to the Earth than the Jupiter, which means the effect of gravitational field strength of the Sun will be larger on the Earth. So it gives like more force or more energy for it to orbit around the Sun. So you can write the orbital speed of the Earth is greater than that of Jupiter because the Earth is closer to the Sun than Jupiter is. So you can also write gravitational field strength decreases as the distance increases. So this is the end of the paper, and good luck with your studies.